Hi, and welcome to Module 4.4 of Digital Signal Processing. In this module, we will explore how Fourier analysis applies to the three different classes of signals that we introduced in our course, namely finite length signals, periodic signals, and infinite signals. We have already looked in detail at the case of finite length signals, where the Dft is the Fourier tool of choice. We have also shown in passing that for periodic signals, the Dft extends naturally into the Dfs, which is the natural representation for periodic sequences. And in the rest of the lecture today, we will introduce finally the Dtft, which is the Fourier tool of choice for infinite length sequences. In the rest of this module, we will use the Karplus-Strong algorithm, which we first saw in Module 2.3, to illustrate the key points of each different Fourier representation. Let's start with periodic sequences. An n-periodic sequence has only n degrees of freedom, and the DFS captures the situation by providing us with a spectral representation for the sequence that only has n distinct Fourier coefficients. We can illustrate these points more in detail with the help of the Karplus-Strong algorithm. You remember how the Karplus-Strong circuit works. You have an input, you have a delay line of length big M, and an attenuation factor alpha. As the samples go in the circuit, they get pushed out to the output, and they get pushed also to the delay line. They will stored here and output at the other end of the delay line after big M samples, where they get attenuated by a factor alpha and summed to the current input. If we were to describe this mathematically, we would have what we call a difference equation that relates the current output to the past output that has gone through the delay line, so an output delay by big M, scaled by the attenuation factor, and sum to the original input. We can use this circuit to generate a simple periodic signal, and to do that we choose an input signal, x, that is non-zero only for n between 0 and m. That means that x of n is actually a finite support sequence, and that's why we use the overbar notation. It will only have big M non-zero samples, and it will be 0 everywhere else. Then we choose alpha equal to 1, so that there will be no attenuation in the loop. If we input this signal to the Karplus-Strong circuit, we will see that the output consists of a periodic signal where each period is constituted of the M non-zero samples of the input finite support signal. Suppose, for instance, that our finite support signal looks like this, has a non-zero support of 32 points, and over the support it looks like a straight line, and it's 0 everywhere else. So if we use this as an input to the Karplus-Strong algorithm, we will get a periodic repetition of this shape, which overall will look like a sawtooth wave. If we take the Dft of this signal, considered as a 32-point finite length signal, the Dft will look like this. Computing the exact value of the Dft coefficients is left as an exercise. Just note, for instance, that the coefficient in 0 is 0 because the signal is actually centered around 0, so its average is 0. What happens then if we take the Dft of two periods? So we consider the first 64 points that come out of the Karplus-Strong algorithm, and we take a Dft of this. Well, if we go through the math, or even if we put this into a numerical package, we will see that the shape of the Dft coefficient, the envelope, so to speak, is the same as the one for just the first 32 points. However, for every Dft coefficient, there is an extra Dft coefficient with value 0. In other words, the Dft coefficients have been interleaved with 0-valued coefficients. To get an intuition as to why it is so, let's go back to the definition of Dft. Each Dft coefficient will be the inner product between the appropriate basis vector in the Fourier basis for C64 and this signal that we see here. So let's see graphically how these inner products are computed. Let's start with the first basis vector. We will show here in blue just the ideal shape of this basis vector. We don't really care about the real and imaginary part because we're just interested in the structure. The first vector is just the constant 1, and the result of the inner product will be the non-normalized average of this signal in red. We know the average to be 0. The same holds for two periods, so the first coefficient is 0. For k equal to 1, we have the first basis vector, and this will be a sinusoid that will span a full period over 64 points. What that means is that the first 32 points will be multiplied by a shape that is exactly the inverse of the shape for the next 32 points. And so this sum of the inner product plus this will give 0. For k equal to 2, on the other hand, the Fourier vector will span 2 periods over the space of 64 points, and so here we simply have twice the same thing. This half of the inner product will be equal to the second half, and the Dft coefficient will be twice the original Dft coefficient. For k equal to 3, we have another situation of antisymmetry between the first part of the Fourier vector and the second part. And so these two parts will cancel each other out. We can see that in general, all odd indexed coefficients will be 0 for this 2-period signal. So we can prove this for an arbitrary number of periods. Suppose y of n is a finite length signal that is composed of L repetitions of the same big M points. So we said that over bar x of n is a finite support signal that is 0 everywhere except in a portion here. So we take this portion, this is m points, and we build y of n by putting L of these pieces together. So this would be L of them. The Fourier transform of y of n is simply given by the sum for n that goes from 0 to Lm minus 1, Lm being the length of this signal now, of y of n times e to the minus j 2 pi over Lm times n times k. And k ranges from 0 to Lm minus 1. So this is standard stuff. The only difference is that the length of our signal is Lm. We can split the sum in the following way. We have an outside sum where we span the number of periods, and an inner sum where we go through the points in the period. And so here we simply replace k with n plus pm. So k was ranging over the entire signal. Now we split this into period plus index inside the period. We can do the same inside the complex exponential, and so then we can split the complex exponential, and we see that the inner sum is this one here, and this term depends only on p. So we can bring it forward and have a product of two sums where we have this term here that ranges over the p index and this term here that ranges over the n index, and the two are independent. But now this guy here we've seen before. This is exactly the same formula that we used to prove the orthogonality of the Dft basis. And so we know that this sum will be equal to big L if k is a multiple of L or 0 otherwise. So with this knowledge, we can plug this back into the formula for the Fourier transform of L periods and find out that the kth Dft coefficient will be equal to L times the original Dft coefficient that you could have computed for the finite support signal if k is a multiple of L and 0 otherwise. So given the Dft of L periods, you will have only one non-zero Dft coefficient out of L, and this will be equal to L times the original Dft coefficient. Well, this was a long way to show that once again all the spectral information for a periodic signal is contained in the Dft of a single period. And that's why for periodic signal in the end we use the DFS. So the situation so far is the following. For n-point finite length signals we will use the Dft. For n-point periodic signals we will use the DFS. One category is missing, and that is the category of infinite length non-periodic signals. We can use the Karplus-Strong algorithm to generate one such signal simply by putting the gain factor alpha to less than 1. In this case, we will have an infinite length signal that is non-periodic because for every repetition of the m-point sequence, the gain factor will decrease. So the first period will be unaffected, the second period will be scaled by alpha, the third period will be scaled by alpha squared, and so on and so forth. So what is a good spectral representation for this signal? We can start with a Dft, and we can see what happens when the length of the signal goes towards infinity. Intuitively, the fundamental frequency in Cn remember, the fundamental frequency of the Fourier basis in Cn is omega equal to 2 pi over n. As n goes to infinity, omega becomes smaller and smaller, and the set of frequencies in the 0-2 pi range becomes denser and denser. In the limit, the set of multiples of the fundamental frequency 2 pi over n will become so dense that we will try to replace this by a real valued variable omega, and this real valued variable will span the 0-2 pi interval. So if we replace that in the formulation for the Dft, we get a sum now over all the points in the signal, and instead of having multiples of the fundamental frequency, we have a real variable. Does this make sense, mathematically at least? So let's try and give a formal definition of what we call the discrete time Fourier transform, a Fourier transform geared at infinite length non-periodic signals. We require that our infinite signal is square summable. That means finite energy. It's a reasonable requirement to prevent summations from blowing up. We define now a function of a real valued variable omega, and remember this is a function, not a sequence, and the definition goes like so. F of omega is the sum for n that goes from minus infinity to plus infinity of x of n times e to the minus j omega n. When this value exists, we can actually invert it and retrieve our sequence values by taking the integral from minus pi to pi of f of omega e to the j omega n in the omega, and normalizing the integral by 1 over 2 pi. It's easy to verify that this is so if you replace f omega inside here by this definition and invoke the fact that x of n is square summable. Now, f of omega is 2 pi periodic. We can see that because it depends on e to the minus j omega n, and this animal is 2 pi periodic in omega. To stress the periodicity of the Dtft, instead of writing f of omega, for a sequence x of n, we will write the Dtft as x of e to the j omega. So, although the free variable is omega, we will write e to the j omega as the argument of the function. This will remind us that this is a Fourier transform and that it is 2 pi periodic no matter what happens, because the argument of the function is 2 pi periodic. Another difference with respect to the Dft is that for the Dtft we choose the minus pi interval as the representative interval for the transform. So these are conventions of a historic nature, and although they're a little bit confusing, it's particularly unfortunate, for instance, that the difference between Dft and Dtft is just a t here. We will preserve the nomenclature and the conventions in order to be compatible or congruent with the DSP literature out there. So let's look at an example of Dtft. Let's take a simple sequence, an exponentially decaying sequence. We know the sequence from the introduction to this class, and we know that it is a non-periodic infinite support sequence. When alpha is less than 1, we also know that this sequence has finite energy, so we can compute the Dtft. We do that, so we write the formal definition. This is the sum from minus infinity to plus infinity of x of n times e to the minus j omega n. Here we use the values for the sequence. The sequence is one-sided. There's a unit step here, so that means that the index of the sum will start in 0, and for n equal to 0 or larger, the value of xn will be alpha to the power of n. We can collect the two powers under the same exponent, and we can see that this is simply a geometric series with ratio alpha e to the minus j omega. And so the result will be in the end 1 over 1 minus alpha e to the minus j omega. The magnitude of the Fourier transform is easy to compute. It will be 1 over 1 plus alpha squared minus 2 times alpha cosine of omega. And when we plot this, remember now the convention is that we're plotting frequencies from minus pi to pi rather than from 0 to 2 pi. So the positive frequencies will be on the right hand side of the frequency axis. The negative frequencies, the one that turn clockwise, will be on the negative side of the frequency axis. The low frequencies will be now centered around 0, and the high frequencies will be on the extremes of the band. With this convention in mind, we can look at the spectrum of the exponentially decaying sequence, And it looks like this for, say, alpha equal to 0.9. So it's a signal that contains energy in the frequency domain, mostly around the low frequencies, of course, because it moves rather slowly to 0. However, never forget the inherent periodicity of the Fourier transform. If we expand the frequency axis outside of the minus pi interval, and we can certainly do that because omega is a real valued variable, what we find is that the shape of the spectrum repeats outside with a periodicity of 2 pi. So the fundamental interval is this, but as we plot outside, we get further copies of the spectrum. Okay, again, fundamental interval, first repetition, second repetition in the positive axis, and same thing on the other side. So let's go back to the Karplus-Strong algorithm, try to generate a non-periodic infinite support signal, and then compute its spectrum according to the new Dtft paradigm. So we start with the same shape as before for the initial data for this Karplus-Strong algorithm. Since we're going to be precise in the derivation of the spectrum, it is useful at this point to look at the analytical formulation for this shape. So x of n between 0 and 31 is equal to 2n divided by big M minus 1, where big M in this case is 32. If we put a decay factor in the Karplus-Strong algorithm equal to 0.9, you see that the repetitions generated by the Karplus-Strong algorithm have an exponentially decaying envelope, and we can express the output as alpha to the power of the floor of n divided by big M that multiplies the periodic signal obtained by putting copies of the pattern we saw in the previous picture, one after the other. And all of this is multiplied by the unit step because we assume that the signal starts at n equal to 0. So 0 everywhere here, and exponentially decaying sawtooth wave for n greater than 0. Analytically, the Fourier transform of this signal can be computed like so. Remember the definition, so y of e to the j omega, the Dtft of the signal we just showed in the picture, is equal to the sum for n that goes from minus infinity to plus infinity of the value of the signal in n times e to the minus j omega n. Just like we did before, we split the sum into two parts, an outer sum that spans every quote-unquote repetition of the basic shape, although of course this time the signal is not periodic, so each repetition will be scaled by a different factor, and an inner sum that goes inside each repetition. Inside each repetition we have the values for the basic pattern and alpha to the power of p, an exponentially decreasing gain factor that creates the decaying envelope. We can split the exponent in the complex exponential again as p big M plus n, and by doing so we can split the sum into the product of two sum. The first term is something that looks like a Dtft. Notice that the index is p and we have alpha to the power of p that multiplies e to the minus j omega big MP. So if it wasn't for this big M here, this would be a discrete time Fourier transform of a sequence that starts in 0 and goes to infinity and whose samples take the value alpha to the power of p. Namely, this is the Dtft of an exponentially decaying sequence, except for this factor here. We'll see how to take care of this in a second. The second factor is equal to the Dtft of a signal that is equal to the basic pattern from 0 to big M minus 1 and 0 everywhere else. So we can write this as the product of two Dtfts. The first one is the Dtft of the exponentially decaying sequence that we saw before. And the factor of M in the exponent propagates to the argument of the Dtft and simply means that we're contracting the frequency axis by a factor of m. It's just a rescaling of the frequency axis. The second term we'll compute in just a second. So let's look back at what the Fourier transform of the exponential decay looks like. The fact that there is a factor of m in the exponent simply implies that there is a rescaling of the frequency axis. So we're contracting the frequency axis by a factor of big M. But be careful, because this contraction will actually have to take periodicity into account. So when big M is equal to 1, we have the standard spectrum of decaying exponential. When M is equal to 2, we're bringing in 2 copies of the spectrum inside the minus pi pi interval. So what before was periodic over 2 pi now becomes periodic over pi. And when M is equal to 3, you will have 3 copies of the basic spectrum that fall into the minus pi pi interval, and so on and so forth. This is, for instance, the case for M equal to 12. Now, on to the second term of the product. As we said, that was the Dtft of a finite support sequence that is linear between 0 and big M minus 1. The result is a little bit ugly and a little bit cumbersome to derive, so we'll leave that as an exercise, and we'll put some slides in the end to detail how to compute this. But fundamentally, this is the result, and if you plot the magnitude of this function, you have something like this. In the figure, you have the magnitude of the Dtft of the 32-point sawtooth period that we saw before. This is non-zero between 0 and 31. And indeed, if you count the local maxima here, there are 32 of them. Okay, to compute the final spectrum, we have to multiply the first term, which is, remember, 32 repetition of the basic spectrum of a decaying exponential, times the spectrum we just computed. It turns out that these peaks in A of e to the j omega m align with the local maxima of the spectrum of the first period, so that the final result looks like this, where the peaks of the first term in the product slim down the lobes of the second term. So here we have derived the Dtft, namely the spectrum of an infinite, non-periodic signal that is not a trivial signal. Now, so far we have treated the Dtft as a formal operator, and in the next module we will see how the Dtft relates to the concept of change of basis in an appropriate Hilbert space.